Good morning, everyone. I hope you are doing all well. Yeah, hope people who are struggling with traffic will arrive soon, more people. Uh, so now we start. Now we have today three talks, poster session, and then there will be spotlight talks. There will be 7 spotlight talks afterwards after the launch. That is the general schedule. And the first talk is by Dr. Ferda Ofli on advancing geospatial AI for real-world challenges. Ferda is a principal scientist at QCRI. His research lies at the intersection of computer vision, machine learning, and remote sensing, with a strong emphasis on applications for social good, particularly in disaster response and crisis management, also on sustainable development. He has authored more than 80 publications in top-tier venues and has received multiple awards, including AAI Deployed Application Award and Outstanding Reviewer Award from CBPR. Yeah, so I'm very much excited to look forward to his talk because I know him for a while on his exciting works on disaster management. So without the delay, let's welcome Ferda.
Thank you, Danda, for the nice introduction and the opportunity. It's a great pleasure to be here, and good morning, everyone. First day of the conference is always more exciting than the rest of the days, but thanks for showing up early here. So today, like Danda mentioned, I'm going to talk about how real-world problems can lead to cutting-edge AI research. And it's going to be sort of a follow-up to yesterday's last talk by Yanis, where he talked more about disaster forecasting in the preparedness stage. My emphasis would be on the time-critical setting like a disaster response, basically where every minute matters. But I'll start with a brief personal story. So I was visiting my grandparents in Izmit for the summer holidays when the 7.6 magnitude earthquake hit the region. And the earthquake lasted about 37 seconds, and those 37 seconds were the longest and the most terrifying of my life. In the aftermath, we spent several nights in the makeshift tent outside in the park next to the building, and this was one of the devastating, like deadliest disasters in Turkish history, leaving more than 18,000 casualties and half, like quarter of a million people homeless. And for me, it was also the year where I was studying for the university entrance exam, which is a stressful milestone, made even infinitely harder by the weight of such a tragedy. And the following year, I began my studies at Koç University in Istanbul with full scholarship. My family had mixed feelings about me moving there because at the time, many thought that another major earthquake would soon strike Istanbul, and then they were scared to go there. And I was young and a bit careless, so I set those fears aside and moved anyway. And it turned out to be one of the best decisions of my life. Because at Koç, I met brilliant professors who sparked the early curiosity for research and helped me build both the technical foundations and the mindset of a scientist. I started with my undergrad studies there, and I went on the PhD studies, and my PhD studies were impactful, and then they opened the door for the next chapter of my journey, which was my postdoctoral years at UC Berkeley. This period was more of a growth and widening horizons. I was immersed in a intellectually vibrant and interdisciplinary environment. I collaborated with leading researchers, deepening my technical skills while also expanding my global perspective. And at Berkeley, I also learned to take risks and pursue new directions without fear of failure. And with this mindset, the idea of contributing to a nation's bold dream of transforming into a knowledge-based economy drew me to Qatar. Basically, I joined the newly founded Qatar Computing Research Institute when it was still its early years, like very much like INSAIT today. And what began as an effort to create a local impact soon grew into a broader mission. I started working on projects with global reach and relevance for the greater good. And then over the years at QCRI, we have leveraged non-traditional data sources ranging from social media, text messages, and images to Earth observation data to build systems capable of performing time-critical tasks like rapid damage assessment, urgent needs assessment, situational awareness. And these systems have been deployed during major disasters in close partnership with humanitarian agencies like UNOCHA and UNDP, among others. And through these efforts, we've made significant contributions or made significant progress in bringing the power of AI into disaster response and management. But just 2 years ago, roughly 14 years after the Izmit earthquake, there was Turkey was struck again by not one but two consecutive earthquakes that devastated multiple provinces, spanning nearly 350,000 kilometers square. And I checked, this is like 3 times as big as Bulgaria. And then the disaster claimed more than 50,000 lives and impacted, left 1.5 million people homeless. This was an unprecedented tragedy for sure. But what kind of pained me most, despite my years in the domain, was the persistent challenge in coordinating response efforts, from rescue operations to aid distributions. Roads were blocked, not by debris, but by overflow of volunteers to get to the region and slowing down unintentionally the operations, basically. And heartbreaking images circulated on social media showing piles of aid like food, clothes, and tents and blankets discarded by the roadside because they couldn't make to the actual places where people were in desperate need of them. So yes, yes, we made significant technological advances in disaster response and management in recent years, but at times it still feels like we're in the Flintstones era, and that we need a long way to leap forward to the Jetsons era. And we must work toward, I mean, this system doesn't exist, but we must work toward a unified system that can automatically detect damaged buildings and assess their severity levels, that can identify blocked roads, and that can monitor shelter areas and aid distribution activities, and also prioritize the response efforts based on the population density, among other critical tasks. And we're not there yet, and how can we get there? What are the challenges? So I'll argue that we need these 4 things. So we need to use all the data available out there, like everybody yesterday mentioned. We want multi-source, multimodal, anything that's out there. We need to tailor our models to dynamic disaster contexts. Out of the box, they don't understand enough. And we need to increase the geospatial awareness of our models so that we can do routing and planning activities more effectively. And last but not least, we need to ensure that our models are robust to distribution shifts and can generalize out of the box. So start with the first point. What can we achieve by triangulating disparate data sources? So now I'm going to talk about one of our recent projects where we combined different data sources like remote sensing, social sensing, and geospatial data, and to do exposure, to map exposure, damage, and urgent needs during flood events. And remote sensing provides a nice bird's eye view of the impact overall, and then combining with social media has the promises more fine-grained insights about what's going on. And then geospatial data complements them with significant information about understanding vulnerabilities in terms of people, locations, roads, buildings, so on and so forth. And these data sources have different spatial and temporal characteristics, and how do we bring all of that together? So we proposed this complex system to process all these different data sources. Don't worry, I'm not going to go into details of all of the components there. I'm just going to highlight like the most important components, one being the satellite imagery processing pipeline. We didn't do anything groundbreaking there. We trained our own UNet model with the publicly available data sets out there, Cloud to Street, Microsoft Flood dataset, and NASA digital elevation model data. It's probably outdated now, but at the time it was enough to do the job for us. And on the social media image processing side, we did something more involved. We created a large-scale data set of disaster images labeled across 43 incident categories and 49 place categories. The idea here was to capture a disaster, an incident scene like car accident in various scene contexts, because when you search Google for car accidents, you probably get a lot of these car accidents on highways, but then you're missing out car accidents on the mountain roads or at critical infrastructure facilities. And so we had this pairing of incident and place labels to diversify the data set. And the model we trained on using this data set, we call it incidence model, proved really useful in filtering out the noisy social media data. So we tested the model on several of the historical data sets that we had from Twitter, and the performance boost was significant with respect to the baseline. And on the social media text processing side, this was our first attempt to use like an early version of an LLM. Remember, this is in before 2022. So BART was like the model to go, and then we, instead of using the old school fully supervised models with closed set of classes, we went for zero-shot classification where we had more freedom with how to choose the candidate labels. And then we used this for urgent needs assessment based on citizen reports. And then we put all of this together, the system, and we deployed it during the devastating floods that hit Pakistan in 2022. It affected 33 million people across the 1/3 of the country and left more than 1,500 people there. And so just some insights using the system. So using the satellite imagery analysis, we had a good initial understanding of the impact of the disaster, like the bird's eye view of which areas were hit hard, and then we were able to identify that Sindh was the most impacted province. And then we coupled that with geospatial data like population density maps, because knowing that an area is flooded, it doesn't mean maybe it's in a rural area, nobody lives, so you don't worry much, but if it's a highly populated area, it's more important. So combining these flood mappings with the population density maps allowed us to identify hard-hit communities like districts across the country. And we further did a segregation of this analysis into different age groups, which then allowed us to kind of ensure tailored response efforts for vulnerable age groups like children or elderly, which may have specific medical care needs or like evacuation support in a sense. And using the text model that I mentioned before, we created this heat map of urgent needs across various types of needs and districts. So it's easy to see, okay, who is needing the most shelter and then donations. Then the rescue efforts are maybe needing more support in some other district in Pakistan. And on the image analysis, social media image analysis side, this is just to illustrate how the complementary nature of the ground level images. So we know there's some flooding here, but we don't know whether it's like knee level, hip level, or shoulder level. And ground level images tell us that, what is the severity. And using the incidence model, we were able to identify like flood scenes and other general damage scenes in different high-level scene contexts like residential areas. We were able to identify flooded and damaged streets, and then also identify critical infrastructure affected by floods and other types of damage, and then other damage scenes were also provided. We put all of that together using our geolocation inference pipeline back on a map. This is like the citizen reports from social media, and this is helpful for responders to prioritize again which districts are talking about more about their impacts and needs, urgent needs. So we provided all of this information in a dashboard like this to the UNDP station in Pakistan, and they used our dashboard to facilitate informed decision making during the response process. And this is the work that won the Deployed Application Award in AAAI last year. If you're wondering haven't you done anything for Turkey earthquake? So we did a similar study on the Turkey earthquake in 2023. In this case, we didn't use the satellite imagery pipeline. It was a large area. It was a bit overwhelming to handle that. We didn't have the models for doing damage assessment. We focused on the social media sensing pipeline, and we analyzed reports about missing people, shelter requests, help requests, and damage reports from images. And the alignment of, so this is showing the epicenters and the fault lines of the two earthquakes, and the alignment of our findings with the actual event is evident. And we provided this information back to UNDP in Turkey. So this was like a use case which I just illustrated, gave examples of how we can leverage different disparate modalities to do situational awareness and provide actionable insights to disaster response. And it was our first effort to also use an LLM out of the box, but can we still say that LLMs, like LLMs, VLMs, remote sensing foundation models are here to the rescue for disaster response purposes? So we were wondering, we wanted to understand their weaknesses and strengths for our particular use case. So that's why we decided to do a benchmarking of LLMs. I'll start with the LLMs. Here we use one of our publicly available data sets that has social media data from 19 different disasters. And then we analyzed zero-shot and few-shot classification performances of proprietary models like GPTs and open weight models including Llama 3, Llama 2, and Mistral. And so the zero-shot prompt looked like this. I'm not going to read it, but we basically provided category names and definitions, and then the few-shot version of the prompt included some examples for each categories. And the findings is collected in this huge table, which we don't need to look at. I'm going to summarize the findings in other plots. So basically, proprietary models outperform the open weight models by a significant margin. They got close to a fully supervised baseline. This is like supervised training, so zero shot, it's not that bad. And the GPT-4o is the winner, the green curve here. And one interesting finding is that there's no consistent trend in performance with the additional more shots. So we increase the shots, but we generally see kind of a drop in performance, and that needs to be explored further. So in terms of disaster type analysis, we wanted to understand if there are biases towards certain disasters. On the left, we see the GPT model's performance. It looks like they perform well on the earthquake type of disasters, and it performed weaker on the floods. And this doesn't necessarily need to be the case. From an emergency response perspective, you care equally about earthquakes and floods in a sense. So there's like a gap that needs to be fixed with the existing LLMs in terms of different disaster types. The situation is worse on the open weight because the overall low performance. So there's kind of there's more work that needs to be done there, but at least they're equally worse for all the all the disaster types. Information type based analysis, this is where we have the category labels of the tweets, and then we analyze if there's certain biases towards some certain classes. And just the first look, we see that proprietary models are performing weaker on the displaced people and evacuations and requests and urgent needs classes. These are very important classes that you want to perform highly if you want to do an effective disaster response. Similar on the open weight side, we see generally like exacerbated or just increased weakness on the caution and advice and requests and urgent needs classes. And we also looked at if there's any bias between native and non-native English, and it was surprising to see that, I mean, we think these language models solved the language issue, but it is still there. So there was on both proprietary and open weight models, there was a drop in the performance for non-native English text. So that was an important finding. So this work was done in collaboration with OpenAI, and it was published in WWW 2025 this year. So now I'm going to move on to another modality, which is vision. Now we want to benchmark the VLMs for their performance on understanding images in the disaster context. Here we're using Incidence 1M dataset, and where the tasks include open set and zero-shot classification, but I'll just focus on the zero-shot classification results. And we have one proprietary model, GPT-4o. On the open weight side, we have Lava with Mistral, Lava with Vicuna, Llama 3.2, Pixtral, and Quen to 72 billion. And so we kind of looked at two types of prompting. One prompt where we just provide the list of incidents without providing any more context. So we just prompt the model that they're going to just analyze some of the images that are taken during disasters. And we ask them this is the list of categories, and then give us what you think you see in the picture. And in the second scenario, we did a bit more, and we provided a description of each category to provide more context, to help the model to understand what we mean by blocked, for instance, because it's maybe ambiguous, and I don't want the model to say it's blocked when it sees a basketball photo from a basketball match. So this is again a large table with all the results, and I'm gonna just move on to talk about like details of the findings. And these are just summarizing all the table with the box plots. And first finding we can say is that GPT-4o achieves the best overall result. But Quen 2, 72 billion is a close second. And all models actually seem to fail terribly, almost like very poor performance on some incident category. On the other side, they don't exceed 0.8 F1 score on any other category. So this is a limitation that needs to be improved. And overall, we see, so this is short prompt, long prompt, short prompt, long prompt kind of ordering. We see a drop in performance when we use longer prompts for the smaller models, open weight models. And again, we wanted to do a category-wise evaluation, whether to see if there's some classes that the models do really well. And based on our findings, these are showing the top 5 and bottom 5 distribution of the incident categories that show up in these top 5 and bottom 5 locations. And most reliably detected categories include floods, airplane accidents, thunderstorms, volcanic eruptions, and snow scenes. And the least reliably detected categories include van accident, derecho, mudslide, mudflow, and tropical cyclone. And doing a more systematic comparison of short versus long prompt evaluation, this is the orange bars are showing number of cases where the long prompt yields better performance than its short prompt version. And looks like the long prompts help with rare or ambiguous categories like derecho, firewall, blocked, van accident. And for many other categories, long prompts offer little to no benefit and even cause performance drops because you see the blue bars are larger than the orange ones, so short prompts is better. Our explanation for this is that when we provide this additional context, we improve models' precision in a sense by making the definition more specific, but then we sacrifice from the recall because the model has a more general understanding. By giving a specific definition, we kind of sacrifice from recall, and overall it looks like it's hurting the F1 performance, F1 score. And another task that we could benchmark the image processing is this visual question answering for disaster scenes. This is very recent work, an ongoing work. So we created a benchmark with 3 types of questions, basically multiple choice, binary, and open-ended. So we wanted to ask things like, we didn't want this to be too trivial. So the level of flood water compared to the height of the submerged vehicle visible in the image, and then they could select all that apply. So it's a multiple choice, but there might be more than one correct answer. And the binary question is usually, is this person on fire, yes or no? And we want, from the disaster response perspective, it's a no. from a show perspective, they might be on fire, but that's not what we want. And then how many lanes on the road are blocked, and this is an open-ended question. We expect model to say 2, both, similar things like that. So the process for this is that we sample some images from our existing data sets. We were careful to choose some hard negative examples, very, very difficult examples, also clear examples, because we don't want always hard negatives to really be fair in judging the models. And then we asked GPT-4o to generate 3 questions for each question type category. And then we had human evaluations in 2 rounds. The first round looked at the questions generated, they modified, and then maybe fixed some answers, and they filtered trivial ones. And then the second round, these corrections were confirmed by more expert people, and then some more interesting questions were added by humans. So we didn't always rely on the GPT-generated ones. Then we had a benchmarking box here. Then we used judge as like LLM as a judge to evaluate responses. So some statistics about the data set. So we have over like almost 1,400 images showing different disaster scenes. And then these are coupled with 4,400 questions with fine-grained domain-specific reasoning-related questions, tasks. Then the distribution of the questions to different types. And we did benchmarking of GPTs. And on the open weight, we used Malmo, Llama 3.2, Pixtrail, Mistral, and Quen. Initial results look promising. They are not doing terrible. The performance, like the accuracies for the yes or no questions are ranging from 86% to 91%. Open-ended questions, the performance is slightly lower. It's a more difficult task, but it's still reasonable. The highest is 0.83 accuracy. And then on the multiple choice questions, again, the best performance is around 85. And there's room for improvement. So these are good starting points, but they're not hundreds. So we can work more on these things. And also, maybe we need to go back and check the data set if it's challenging enough. So there's, as I said, this is like a first version of this work. And for now, based on these results, GPT 4.1 mini achieves the highest scores overall, and but Quen 2.5 is getting really close. So, and even surpasses the GPT-4o mini. GPT-4o mini results are lower than Quen results here. And we wanted to do a different, similar type of analysis, like in terms of disaster type. Do we see any weaknesses? This is not very kind of helpful. For the binary questions, they seem to be in the same ballpark across the board. Accuracy varies uniformly between 0.8 and 0.9. And for the open-ended questions, it's a bit more chaotic. There's like wildfire is quite, the performance changes quite a lot for wildfire questions. And on the multiple choice, it's overall there's the performance is lower, but the variance is similar across different data set types. And just one example, I didn't have a lot of time to search through the results to find better examples, but this was the first example I found this morning. And so this is a picture where we ask the model to name an object the person is handling, and the answers can be cable, wire, wires, or anything, but then along the same lines, but the model, like Pixtrail 12b, says umbrella in this case because it's a rainy scene. So it's not enough to have just one example, but I wanted to show it anyway. But if I present this somewhere again next time, I'll have more examples. So this kind of concludes the benchmarking of the existing LLMs on image and text. And the next topic is about the third point, geospatial awareness. Can LLMs support complex geospatial reasoning tasks? How am I doing in terms of time? I know I'm... Okay, good. I feel like I'm running. I have many slides I wanted to cover. So yeah, time-critical geospatial reasoning during crisis. We like the humanitarian agencies, response agencies often come up with really challenging queries like, can you provide an optimal delivery route for relief trucks starting from location A to location B, avoiding flooded or blocked areas? And this is a dynamic event going on, so this thing may change. Like, so you have to always make sure that there might be cascading effects, and you have to account for that. Another question might be like, if X road becomes blocked, what alternative routes remain to evacuate residents from zone A? And so on and so forth. Basically, these type of queries require complex geospatial operations and reasoning, using various information sources like traffic conditions, topology, road damages, accessibility updates, and so on and so forth. And based on our experience, the LLMs are not there to answer these questions. So we start with even a simpler question like this: which road is closest to the geo-coordinates somewhere in Christchurch, New Zealand? And the answer, you cannot read, I'll read it for you, should be okay, it's here. So Springfield Road. So we asked this question to different models, GPT 3.5, GPT 4.0, Llama, and then the results are like quite far away. So GPT 3.4 said the closest road is Main North Road, which is 20 kilometers away. Similar situations also observed for the other models. And our goal is to have a model that really returns the correct answer. Maybe not always, but most of the time. So to this end, what we do, we created this pipeline for geospatial knowledge representation learning, where we leverage OpenStreetMap data, which is very rich in terms of road network and a lot of metadata around it, number of lanes, speed limits, and road types, and so on and so forth. So what we do is we take that data and we turn it into structured textual format, which we can then use for pre-training and fine-tuning the LLMs. So we think about some core representations that kind of just capture the factual knowledge about the network, the road network. And then we also create some structured text that has more information about the spatial reasoning in terms of directions, distances between locations, and so on and so forth. So we use this data to pre-train a model and then do a SFT on the spatial reasoning part. And then we evaluate it on different cities. We looked at like cities from different regions, Los Angeles, Christchurch, and Metro Manila. And here we're looking at the performance achieved by the best model. We have like different versions, our best model versus best baseline. I showed you the baselines with the raw are like completely off, they are 0. Here our best baseline is where we kind of allow the model to cheat. So we provide the model a kind of short listed of choices. Okay, I'm asking you to give me the nearest road in this neighborhood, and then these are like the best options, 5 best or 10 best options you can choose. Even then, the best baseline is doing significantly worse than our models in these 3 cities. And then the tasks include like metadata prediction, road length, speed, and lanes. And then we also have special calculations like distances and directions. And then we have another task for road retrieval for standard and directional. So can you give me the nearest road in the north direction, in a sense? So these are the axes represented by these tasks. So this is where our first attempt to fine-tune or develop an LLM model that's improved in terms of geospatial understanding. We heard a lot about the agentic approach, so we thought, yeah, maybe we can solve this thing by as an alternative approach using agents. So this is now, we can use agents, LLMs as agents for geospatial tool calling. And the first kind of try we had was like asking GPT-4o Mini to give us nearest hospital while avoiding damaged roads, hazard, and it just gave us, this is the result returned by the model, it just gave us like a direct bird fly distance. And then our method, which I'm going to describe in a bit, gave us some proper routing plan. And then not only that, it was just a bird's eye flight, actually gave us a restaurant somewhere else. So we were asking for a hospital, but we got a restaurant in return. And so this is very experimental. So what we did is we are inspired by FEMA's incident command system, which defines organizational structure and elements of the response efforts. So it's like similar to a hierarchical, a multi-agent system for geospatial intelligence, where we have a supervisor that kind of gets the query from the user, and it kind of dissects it into different tasks, and then at we have like geocoder agent, facility finding agent, route planning agent, damage mapping agent, and infrastructure mapping agent at the expense at the use of the supervisor model here. And just a quick, yeah, it's hard to read, I'll try to read, but just a quick kind of run over the model, how it works. So here, the query, I forgot to read the query, I think it's important. Yeah, let me read it. Create an evacuation route from Rue La Fleur to Gymnase Saint Vincent with a stop at an operational gas station that avoids all hazards. However, if stopping at a gas station adds 3 kilometers or more to the regular fastest route, simply route directly to the gym. And then what happens is supervisor takes this query, and then it first finds the locations, toponyms, the location mentions, and it asks the geocoder agent to identify where these areas of points of interest, and then the geocoder agent returns the points of interest, and then supervisor then routes subtask of finding operational gas stations because that was in the query. Then it asks the facility finder agent about this. Can you give me the available and unavailable fuel station stops? Then the supervisor gets this feedback, and then another task is to identify the damaged roads because they want to, it needs to avoid those regions. So that's where it contacts another general that knows, another agent that knows about damaged areas. So it returns results. So and then finally, with all this collected information from different agents, the supervisor asks the route planner to come up with a route, and then it returns, like it comes up with 2 routes, one making it to the gas station and then avoiding the damages, and then one that kind of without reaching there and then making the distance. So you need to compute both routes because the query requires the assessment of if the additional road is more than 3 kilometers, then you have to decide which one to choose. In this case, the one route is 10.47 kilometers, and then the other one is 13.62 kilometers, which is slightly over 3 kilometers. So basically, you're gonna skip the gas station, and then you're gonna just go back to directly to the gym. So this was more like a qualitative analysis of the system. We don't have, we're working on creating some kind of test set to qualitatively assess this, and this is just one use case. And but I think this is quite promising, and in the long term, what I believe is the combination of both a foundation model that's geospatially aware embedded into these agentic systems, because you may need that for some of these subtasks, maybe not for the supervisor, but for some subtasks, they can benefit from having a more improved LLM model. And with that, I'll move on to the 4th point, where I was talking about the distribution shifts and the generalization to, in general, like the real world conditions. So what do I mean by this? You know, an earthquake that hit Nepal in 2015 looks different than an earthquake that hit Italy in 2016. So there is if you have a model trained for Nepal, it's not going to work for Italy. And this is like a very challenging distribution shift, but if you want to look at a more simpler scenario where there's no disaster context, but you just want to do building detection, even for building detection, the buildings look quite different in Greenland versus Madagascar versus Qatar. Where you are on Earth, the buildings look different. Let's say cars look the same. If you want to do car detection around the world, then the images don't look the same. So the cars in Western world with the satellite imagery with better quality, you can detect cars better, but in the Middle East, with the atmospheric conditions, the sun and everything, the image quality is not there, and the cars are hard to detect because they're not always on the roads, paved streets. So there's still a distribution shift that we want to handle. So why is it important to handle distribution shift? Because we train our models based on the IID assumption. So we train on some test training set and test samples. We assume that they're going to come from the same distribution, but that's rarely the case in real world scenarios. So when we have a new test image coming from a different domain, the model tends to make more mistakes, and this is called domain shift. And one approach to tackle this challenge is domain adaptation. If you have time and data from target domain to train, to adapt these models. But remember, we're working in a time-critical situation. We don't have the luxury of, oh, let me wait for data collection from a disaster. So domain adaptation is not an answer for us. So we need the models directly generalize in out of the box. This is a more challenging task, but it's desirable, basically, that we want to have achieved. And domain generalization in image classification has been studied extensively. There are many existing data sets. Most of them are, I would say, in like lab conditions, toy data sets like digits, VLCS packs. And more recently, Wilds introduced more challenging real-world data sets. One of them, they have like medical and other stuff, but one of the real-world data sets that they introduced is a repurposing of FMOW, where they defined the domains in terms of time periods. But we're interested, that's a valid and important point to study, but we're also interested in studying the special shifts, covariate shifts. So that's why we kind of just follow the idea and then repurpose the FMOW for special, for geographic shifts, the domain shift across geographic regions. And this required some careful curation because not all of the instances of classes appeared in all the regions, so you want to eliminate some of the classes and do some data balancing and all that. But in the end, we had a kind of real-world domain generalization data set with 6 domains. In this case, we just defined regions based on the population division of the Department of Economic and Social Affairs in the United Nations. So you may ask why like Mexico is not North America but South America. That's the reason. Just to have some more uniform MITI within the domains. And then we benchmarked existing models on this data set. So this data set was published recently in IJCV. And we provided benchmarks, 3 different types of models, like classical models, ERMs, IRMs, and more recent models like deep coral group DRO, and the foundational model called CLIP OOD, and DG model based on CLIP. And we tested different things. We had a single source training and multi-source training, so we hold out one domain as test, and then we have the option just to use one domain for training, or we combine the domains for multi-source training, and we look at experimental results for that. So the first, I'm going to look at the single source training results. We see a significant drop from ID performance to OOD, and then in terms of percentage drop, these ranges between 20-something to 50 or 60% based for different domains. And in general, ERM, IRM, deep coral, and ground DRO achieve like similar performances in terms of performance drop and the H score, which combines the like harmonic mean of ID and OOD performance, just to have a better compromise between the two. And in this case, CLIP OOD achieves a smaller percentage drop and higher H score for all the domains. For the multi-source training, what we see is we see an improvement in the OOD performance. Not a lot of differences in the ID performances, so it doesn't change the ID performance much, but we see an improvement in the OOD performance across domains. So the percentage drop is smaller. And one interesting finding is that in this case, the CLIP OOD loses its competitive advantage. In terms of H score, it's not outperforming other models. The other models are performing better H scores across the board, basically. And we wanted to kind of explore, like, well, what is the promise that we are getting with CLIP OOD? It's supposed to be foundational model based. And we looked at the backbone. So we took the CLIP backbone and we plugged it into ERM, like the typical cross entropy we do with empirical risk minimization. And we used different backbones with ERM and with CLIP OOD. Interestingly, under equal backbone conditions, actually, ERM outperforms CLIP OOD in both single source and multi-source setups. So then all of a sudden, the promise that the CLIP OOD was giving on these toy data sets is gone. went on this new data set. And this is again in line with the domain bed authors, like when meta researchers organized the existing data sets and created a domain bed repository for studying domain generalization. Their claim was that all these new domain generalization methods were not outperforming ERM, and we're seeing the same thing here. So it's I think the domain generalization field needs more challenging, more realistic data sets to really to benchmark their methods against. And this was our exploration in the image classification domain. Then we thought, okay, what is out there in the object detection? And it turns out nothing much. There was only this recent COCO-O data set that was published in ICCV 2023. And it's only a benchmarking data set. You cannot really properly study model training because it has only very few images. And then again, the domains are, I would say, like toy domains. And following the same idea we had for DSGR, we went ahead and we repurposed existing data sets like XView and XBD. XView is a data set with land use, land cover classification labels, and XBD is a disaster damage assessment data set with different building damage severity levels across different regions. So just to, in this case, we changed the domains, the approaches. So we looked at climate zones as our domains on the XView, and we looked at different disaster, like flooded regions and hurricane events as our domains. So climate zones is, I think, understandable. In terms of flooded regions, what we did is we looked at floods in US versus floods in India, Bangladesh, Nepal, that region. These are flood events that are appearing in quite different, like far apart parts of the world where there are differences in socioeconomics and whatnot. And then to counter that, we also looked at hurricane events all in North America to see if there's still some shift between different hurricanes that hit different places in North America in different years. These are all hurricanes happened in somewhere in North America. Hurricane Michael, Hurricane Matthew, Harvey. So we did benchmarking of these models using, again, classical FAST RCM, MESC RCNN, more recent object detection models like Dino and Todd, and then more like state-of-the-art models like Grounding, Dino, and GLIP. We follow the same training and testing setup, single source, multi-source. And in this case, again, there's a significant drop in performance from ID to OOD, and which is consistent with the previous setup for the classification task. And GLIP experiences the lowest drop between ID and OOD performance. So in terms of performance drop, it is the lowest. But the thing is, it's not performing really well on ID with respect to others. So that's why the drop is smaller. But overall, if you look at the H score, it's not the best model. So Grounding Dino is doing much better in terms of balancing ID and OOD performance. This is a single source. So on the multi-source training, it looks like multi-source training in this case enhances both ID and OOD performance. In the classification case, we didn't see much improvement with the ID, but here in the object detection, we're seeing improvement in ID performance as well as in OOD. But the findings is like the same, similar, like Grounding Dino provides a better deal between ID and OOD performance, while GLIP is still kind of the lowest, except for this climate zone. And in the interest of time, I just focused on climate zone findings, but there are more findings. This was a CVPR paper that we presented this summer, 2025, and more details are in the paper, or I can discuss later. Just a few slides to talk about like future directions. I mentioned that we had this project where we combined like disparate data sources, where we basically just overlaid them in a sense, but we didn't have a proper like analytical, like spatiotemporal integration of these things. Maybe we can use insights from spatial-temporal statistical modeling, where we have these like social sensing data layer, the remote sensing data, flood impacts, and then other geospatial data layers into a more scientifically studied, where we can really borrow knowledge from the neighboring the regions, and if there's like a temporal aspect, we can also borrow information from previous time instances here. So this is something I think that needs to be done. Also, we need to go into more fine-grained damage assessment where we can make decisions at the pixel level, because this is important to identify, okay, what is the amount of rubble, or is there anything blocking the road? So we need to really localize the hazard and maybe quantify the hazard. So that requires a fine-grained damage assessment. Maybe answer to those problems is just trying to work on a multimodal foundation model for disaster response in general. If we can bring all of these modalities like satellite images, aerial images, and ground level images together with social media text or other official reports that we can get from GDALT, like news articles and stuff. And then that can allow us to do all these different tests that I mentioned earlier. And maybe having this model can allow us to go more from like predictive analysis, just understanding what's happening now, to answering questions like how should we do things, more prescriptive, where we can have provide like some actionable feedback to response agencies. And maybe even based on this model, we can think of doing anticipatory things where we can use it as a simulation model to think about an unprecedented event. What happened if there's like an unexpected amount of water, raindrop hitting Dubai, which wasn't expecting, and then that created a lot of like disaster in a sense, and you don't know which kind of parts of the city and critical infrastructure might be affected by that. So we can maybe leverage the generative abilities, or to some degree the hallucination effect of these models to our benefit, turn it into a feature for anticipatory decision making. So the takeaways, there's no silver bullet. I think all data sources might be important, especially for disaster response. So it's important to triangulate information from whatever the data is out there. And we have to embrace the changing disaster landscape. It's chaotic with distribution shifts, biases, anomalies. And we have to couple that with geospatial intelligence, because that's what if you cannot put the information on the map, that's not really useful for emergency response agencies. And out-of-the-box generalization across geographies and disaster events is also crucial, so that we don't need to fine-tune or develop new model every time a new disaster happens. So with that, I'd like to just acknowledge my internal, external collaborators, and I'll leave you with this thought. Thank you.
Yeah, thank you very much for this very insightful talk. With that, we are open to questions.
Thank you for the wonderful presentation. I have two questions. First is if it's possible to share the slides. I saw a lot of people were taking screenshots. And the second,
yes.
Thank you. I will ask later again. The second one is I really like the idea that we should do prescriptive analysis, but in that case we need to work together with government and municipalities, because it's like not only what should be done, but also what can we do, like in terms of budgeting and programs and stuff. Are you working towards this? Are you working with governmental structures?
Yeah, I mean, in the beginning of my talk, I showed that we always work with some stakeholders, government agencies or humanitarian agencies. They are always in the loop. And maybe I didn't emphasize it enough, but we're not replacing them. We're providing assistance. So everything we do, we are providing that as feedback to the actual people on the ground, so the practitioners then can take informed decisions. So we're not kicking them out of the loop. And especially for prescriptive part, what we can do is make suggestions. Like we don't want to come up with a full-fledged plan where then the robots or self-driving cars can take up. No, it's gonna be a plan that we recommend, maybe a number of plans with some priorities to the responders that they can then choose and maybe customize a bit. So that's the idea. So we're not gonna do everything on our own. The disaster response is quite a sensitive area, like health research. So we kind of don't replace the experts, but we assist them as in the best way possible. And like for the anticipatory AI, I think there's now the emerging idea of like VLAs, vision language action models. So they're more used in robotics space where, okay, you decide the next action is, but we want to turn that more into suggestions. What is the next actionable task to do? And we can have a list of those suggestions, then maybe feedback from the experts, government agencies or humanitarian agencies on those plans, and a scheme for training models, basically, in that purpose. I don't know if that answers your question. Okay, thanks.
Are there more questions? Yeah.
Thank you for your presentation. I guess when it comes to foundation models, which you mentioned, I guess the real question is, do we have enough data to train them? Like to train a model which is like geospatial intelligent.
Yeah.
So
I think the data is there. It's just that I don't have it, but Google has it, or other companies. Like there are other players that have this data. So I didn't provide a lot of solutions. I talked about a lot of challenges and problems that need to be addressed. So some of these challenges can be addressed by the research institutes and academics like us. But then I think the bigger problems at the global level can be requires a more concerted effort. And what was I going to say? Yeah, like we have a lot of data from Twitter, for instance, historical data. We have billions of tweets collected throughout like the more than 10 years of data collection that we had. So we have that. We cannot really use it without Twitter's permission. But then the same data is there with Twitter, social media data, and then they can use it to train this kind of models. And or if anything, they should provide us some collaboration or something. So the bad news about that is when Twitter, the Elon Musk bought it, they closed the API, so it's useless. So most of the things that I presented on the social media side are, the systems are still there, but the data is not coming. There's no data point, so they closed the API. So we're just showing the proof of concept, the opportunities, but the solutions require more organized effort.
okay, thank you.
Thank you.
Thank you for your presentation and for the mission that you're tackling and the impact that you're having on the global world. My question is regarding the difference between the benchmarks on, for example, car accidents and van accidents.
Mm-hmm.
Do you think this is correlated to the difference of how often this happens, and like how equally distributed is the data that you have? Mm-hmm. And in the end, is it more important to have good benchmark for the most often cases, or strive for equality?
Equality?
Not equality, but like equal probability, equal like benchmark for the yes.
Fine. I mean, it depends on what you want to do. If you want to reflect real-world conditions, I mean, there's a long tail in real world, so maybe it's okay to just care for the most dominant class. But then, from a disaster response perspective, even the long tail matters a lot. So you don't want to do that. You want to go for more like a balanced approach, and then benchmarking, depending on the actual task, it's important to go one way or the other. And what was the first question?
About the data set, is it?
Yeah, in terms of the distribution, I wanted to find that slide where, would show explain maybe the frequency of like the data distribution of classes. I couldn't find it. It might be a reason, but then there are also other reasons that we observed, like truck accident. Truck seems like a confusing phenomenon in the US. People call like the SUVs as trucks. To me, it's not a truck, but they call truck. And then when you search Google, you kind of get both like SUVs, Jeeps, and then the actual truck, kind of truck, they're all messed up. So there are some categories that kind of suffer from this conceptual or cultural differences. So for some reason, yeah, truck accidents were quite interesting. And van accidents are related, has like a similar challenge. What is meant by a van is different in different contexts.
Thank you.
Thank you.
Anyone else? Okay, I have one last question. So, in the context when every minutes count, as you said, wondering that what is your take on the data availability? Because if we wait for satellites to provide data, we may need to wait for days.
Yeah.
If we wait for social media, that too also may not immediately be available. Maybe flying a drone, or depending on different kind of criticality, maybe sometimes you can afford to wait, sometimes you cannot afford to wait. And
Yeah.
how do you see that? Where shall we put our bets on regarding the data or processing more for the cases where it's very, very time critical?
Yeah. So that was our selling point when we started working on social media. We spent more years working on the social media pipeline. We recently just started work on the remote sensing and satellite imagery analysis. But in between, we looked at the UAV use cases, using drones to do some of these tasks. And at that time, it was a bit early. We had a data collected from Cyclone Pam in Vanuatu in 2015, I think, with World Bank. Okay, we needed some big entity like World Bank to fly those drones and collect the data. Otherwise, as a research institute, we don't have the luxury. Even now, there's like a lack of, we need the code of conduct. Who can fly these things and how can they collect information? I think there's more improvement these days, which agencies can kind of do this, but it's at that time it was a bit challenging. And like going back to the first point, our selling point was the social media, because it is usually there, it's very real time, it's instantaneous, and yeah, there might be power outage, but then it comes back, and then there's also other areas where there's no power outage, but they can still provide useful information like proxy. So that was our selling point. That's why we went big on analyzing social media data, because it provided that immediacy, the urgency, that addressed that part. But I think in general, with the increasing number of satellites, the delays are probably, hopefully, can get lower. They're not gonna be like in real time in real sense. But because, let's say, drones, getting the people there, the experts to fly, it's gonna take time again. It's just not gonna be real time. So I think I don't have a good answer to this question. It's a big challenge. So social media was very, citizen science was promising, but then it might have also some challenges like the power outages and whatnot. So I think the system should be adaptive. So if whatever is out there now, you have some reports from social media, just start with that. And then whenever you get some drone imagery, you incorporate that, some satellite imagery, then incorporate that. So you don't wait. I think the idea is not to wait.
All right. Thank you very much. With that, let's thank Ferda for his great talk again.
Thank you.
With this, we end this morning, first session of morning talks here. We move to the posters, followed by the coffee breaks, almost combined together, although coffee may start slightly later than the poster. And then we get back here at 11:30, almost in an hour. See you.